If flying is a science, it is also an art. As such, it is important we analyze the state of the art. For more than 2 generations, the riveted sheet metal construction airplane was defined and described as the state of the art. But time moves on and ideas change. There is a new state of the art. It is seamless, aerodynamically smooth and accurate. It's lighter and stronger. It's more resistant to corrosion and better in every way. It's part of a new technology, and it's available to builders now to use. I think we should take advantage of this availability. We're going to explore in a very practical way the methods of working with composite construction using foam, fiberglass, and epoxy. And once mastering its uses, the work of the aircraft builder takes on a new dimension. The art and science of flying takes on a new dimension. What we have here is a sample of 2 small wings. Actual aircraft construction, very similar metal construction and fiberglass construction. They're both the same weight and the same size and provide the same aerodynamic function. Notice the aluminum one has a myriad of stress concentrations. Very low stress in this area, and then high concentrations where rib loads dump into the spar and where rivets are. The composite full core moldless construction, like we use in the home builds, is very uniformly loaded. It doesn't have any ribs, or indeed it has one rib that runs from here to here. It's a full solid core of rigid foam. It's very, very stiff. It doesn't deform under loads. And more importantly, it's very uniformly loaded. The core does not have traps for water to get into. It doesn't corrode as easily as this. It holds its shape better, and it is stronger. We're going to just put it down here and leap up on top of it and show you what happens when it's overloaded. Okay? Ready? The metal one not only failed the spar, but it fails the skin. Under loads, it's very weak. It's very susceptible to fatigue. The fiberglass one, on the other hand, can take extreme overloads. Extreme overloads. And they're both the same weight. Notice the aluminum where the spar ended at this point and went to a lighter spar is where we had a spar failure. Notice also that we have skin failures, wrinkles, buckles, rivets popped out. In general, a lot of deformation going on that's permanent. In general, the composite takes much higher loads, even though it's the same weight, takes much higher loads without any permanent deformation and without any loss of its aerodynamic qualities. The composite is extremely strong. For the same weight, it's a considerably more durable, considerably stronger structure. In general, the composite allows the builder to make a spar that smoothly decreases its thickness instead of more abruptly like you have when you're stuck with various material sizes that have to be riveted together. The composites also are considerably better for corrosion. If you take and dip this whole assembly in salt water, for example, you would totally destroy the structural integrity of the aluminum within just a few hours, actually. In a saltwater environment, both of these structures exposed similarly, you would ruin the metal and not damage the fiberglass at all. The fiberglass does have to be protected from ultraviolet radiation with appropriate paints and ultraviolet barriers. We're going to now define what the sandwich structure really is. The entire airplane is built of various parts that are all sandwich construction. Plate sheet construction, like this piece is very flexible. You can see that it can be flexed, bent. And this is core material, which is very light and very weak. It's a rigid foam that provides support for skins, but it's quite weak and doesn't provide much strength by itself. But if the core material is faced on both sides by high-strength fiberglass-oriented facings, we come up with a structure that is very stiff. And it's made of the foam in the interior with facings on each side and closed out on the ends of high-strength fiberglass, and with the strength of the fibers oriented in the direction that you require the highest strength. You've noticed that these things here are so flexible they can just be bent with your hands like this. This is the same weight piece of sandwich structure, and you can see that it will even support your entire weight. We can both get on here. And this is the same strength as this piece. For the remainder of this program, we're going to show you in detail what is required to build and finish and inspect these sandwich composite airplane parts. We're going to cover the shop requirements, the health requirements, carving of the foam, hot wire shaping of the foam, making the fiberglass layups, inspecting them, and finishing them. So we're going to give you the whole gamut of how to build. Okay, now Mike is going to show you how we carve and shape the core material when we're using urethane foam or PVC foam as core material.
And these are some of the basic tools you're going to require to do this job. The hobby store saw, your basic butcher knife, keep it good and sharp, a piece of coarse grit sandpaper, 40 grit sandpaper, and a little chunk of urethane foam. It also helps to glue some of the sandpaper to a hard block with contact cement. In carving your PVC foam, polyvinyl chloride foam, you lay it out, whatever you're going to cut, if you're going to cut a bulkhead or something, lay it out with a felt tip pen, and then take your little saw and cut the material. It cuts very easily. And if you have to shape the edge of this foam, you can sand it with sand. PVC foam is not difficult to work with at all. The urethane foam is used where we have very compound shapes on the airplane. And you can sand this material with itself. Use the material itself with a tool. By rubbing, you can round the material. You can shape it. It carves very, very easily. With a butcher knife, you just round it off to a nice, pleasing shape. If you're carving the nose of the airplane or something. If you have to make a depression in it, like where the control stick is in the front seat, dish it out a little bit with a knife. Take a piece of urethane and work it in. In just a few seconds, you can come up with a nice, pleasing curve in the foam. The tool takes on the shape of the hole that you're carving. Very shortly you have a nice smooth dished out area where you can lay fiberglass without any sudden changes in shape. A hard block can be used to sand urethane or PVC foam.
The cores for the sandwich structure for flying surfaces are made out of styrofoam and are hot wire cut to shape. As part of our demonstration, we'll be making an actual part for a long easy aircraft, and it'll be the lower part of the vertical fin from about this location down. These are the large styrofoam blocks as they're received. They're rigid foam relatively low-density styrofoam, and they're the core for all the flying surfaces. The rest of the items on the table here are tools required to do the hot wiring job. First of all, we need bags to hold the blocks down firmly while the hot wiring is being done, and these are bags of lead shot. You also need a nice smooth level table. Then straight templates, and these will be used to saw straight cuts in the foam to make good planform sizes. Then the templates themselves for the hot wiring cuts that give you the shape of the airfoil that we're making. These templates have a level line on them so that the twist of the flying surface can be set, and they have little talking numbers, and you'll see how those are used later. To nail the templates on the foam, we use just standard nails. The hot wire itself consists of a voltage control that we can adjust 18 volts roughly, plus or minus 5 volts with a control, and it feeds a current to a very simple saw. And the saw consists of a 2x4 with some steel tubing in it, and tightly stretched between the steel tubing is a piece of stainless safety wire, and we'll be running a current through it at just the right temperature to make the saw cuts. You'll also need for hot wiring a pair of pliers to adjust the tension on the saw, and it's done by cranking on the end here. Okay, now we're going to line up the straight templates so that we can cut a perfect smooth face off of this normally rough styrofoam block edge. We'll carefully put a straight line on it with a square, or we could use a level also to set this line. Then we'll nail on the hot wire template, and we'll do that at each end, and it's important that we leave the template sticking out above and below the foam block. It's important to check the accuracy or the straightness of the templates, and this is easily done by setting a level against it and making sure that they're perfectly straight up and down. This assures us of a perfectly straight cut. We're going to now show you the setup of the hot wire and how to get the right temperature and the right tension on the wire. Both of these are very important for successful hot wiring. We've got the control on, and we are going to now check the speed. We do this by taking a piece of styrofoam material. The wire is very hot, it'll burn you if you touch it. And you press it on there lightly and count, and it should move it should move in an inch in about 4 to 6 seconds. It's a little too hot now, so we'll cool it down a little bit. And wait just a few seconds for the wire to cool down, and push it through and count. 1, 2, 3, 4, 5. We've got about 4.5 seconds per inch of cut. That's the right temperature, and it's important to check that before each cut. Also, the wire must be very tight. We recommend that you string it like this while the wire is hot and keep tightening it until it stops changing its tone. And what we're doing is yielding the wire and stretching it now, and we've got the wire as tight as it possibly can go, and that's the correct tightness. Both temperature and tightness must be checked before each cut. Okay, now we're going to do the facing cut, cutting a straight face. What we do here is hold the wire lightly but continuously against the templates and then move downward. It's not real important that we both go at exactly the same speed, because as we come out of the bottom of the cut, we're both going to hold the wire continuously against the templates, and if there's lag of the wire in the middle, it'll still cut a perfectly straight surface. So I'll be giving Mike some information here pretty quick to tell him how close I am to the bottom so that he'll know to either speed up or slow down. I'm 3 inches from the bottom.
Okay.
2.5.
Okay.
2 inches. 1.5. 1 inch. Half. Quarter. Coming out, and I'm holding the wire, so is Mike, against the template until it pops free in the center. What we've made here is a cut that's absolutely perfectly smooth and perfectly straight. Okay, we've got the foam block now cut to the correct dimension, 8.5 inches here. And now we're going to make a diagonal cut. We're going to lay it out by using a square and measuring back the 3.5-inch dimension. And we're going to carefully place the templates to be able to make this diagonal cut. And this achieves the plan form of the part.
You should be careful that you don't place the nails so that the hot wire can snag on them, particularly when you're cutting an angle. The wire could snag on one of the nails and hold you up.
We have found by careful experience many times that the hot wire will not go through a nail. Okay, actually the hot wire saw works much better if it's closer to the length of the part. We're using much too long of one here. We're going to place it on here and do the diagonal cut much like we did the first cut you saw. We've got 3 inches to go, 2 inches. Again, it's very important to keep it on the template as you come out. That way the lag in the middle will not disrupt the part. It'll be perfectly square. Now we have the plan form shape. This will be the trailing edge of the new part. Okay, now that the hot wire core is set up at the right plan form, we're going to take the template. We already have the template placed on the other side, but this one is placed at the same distance down, and we'll measure down to what's called the level line. And then we'll move it fore and aft until this thing that's called the trim line is exactly located on the trailing edge of the foam block. That will assure that we have the right plan form. I'll put a nail in near the middle so that it doesn't move the trim line as we level the template. Now these level lines are very important because they determine the twist of the wing that we're making. And if the 2 level lines on each side are leveled with respect to each other correctly, then we have the correct amount of twist that the designer has put into the flying surface. So nail it down good so that it's firm. We'll also position what we call a leading edge nail, which is just a nail stuck right on the level line in about that far, and it'll help guide the hot wire into the airfoil in making the cut. Now let's pick it up and take a look at the other template on the other side. It's positioned exactly like this one was. It's the same amount down. The line was leveled with the level. It has the leading edge nail. It has the trim line set right on the edge of the foam block. And now is the time that's very important to take it out and assess it and say, yes, that is correct, because it's very easy to make these backwards so that the sweep of the wing is forward when it really should be aft. And so you should scrutinize 2 things at this point in the game. Scrutinize for sure that that is the correct point, that's the correct airfoil, and that it's sweeping aft at the leading edge like it's supposed to. And also look very close at the nails to make sure that you don't have any in an area where they'll be intercepted by the hot wire. Once that is done, we take the block and get it ready for hot wiring. And what that involves is getting a good weight on either side to make sure that the block cannot move during the hot wiring operation. If it can move by any pressure on these templates, it'll deform the part and cut it incorrectly. This is not real important on such a small piece, but on a wing, this cut may be 40 or 50 inches long. And if they are allowed to move a little bit because they're overhung on the edge of a table or not correctly supported and not correctly weighted right over the templates, then the part will be made incorrectly and will be scrap. We're getting ready to make the important cut now of cutting out the core, the airfoil shape. What we're going to do, first of all, is to check the tension and temperature of the wire, and we've done that. And we're going to move the wire in here, and Mike will count down in inches until we are resting on this nail, but still safely away from the airfoil. When I confirm that my side is in the same position, resting on the nail, he will then move in towards the template. He'll say 1/4 inch, 1/8 of an inch on the wood. And then he'll move up and he'll carefully count these letters, A, B, 1, 2, 3. It's very important that we stay together in sequence, and I'm going to be following by listening to him and keeping my side exactly the same numbers on this side. Very important that we stay in sequence, particularly around the leading edge where it's critical. Out in here where it's relatively flat, it is not critical that we stay exactly together. When we move out of the foam, we're going to continue to rest on the wood until it pops free in the middle to make sure that it doesn't ruin the leading edge by going up or down. Okay, we're ready to go, and Mike will do the talking and I'll do the listening. He knows where his side is, I'll know where my side is and his, because I'm listening to him and watching my side. Okay, let's start
we're
the
going
cut.
into the foam. We're 2 inches from the nail, 1 inch, 1.5, 1 inch, 3/4 of an inch, half an inch, 1/4 inch. I'm resting on the nail.
I'm resting too, go ahead.
Okay, going in, we're 1/2 inch, 1/4 inch, 1/8 of an inch on the template going up. Half A, half B, half 1, half 2, half 3. How's the speed?
Pretty good.
Half 4, half
My job is to follow his numbers and keep a light pressure on the template, not a heavy
6,
one. We don't
half
force the wire,
7,
we just let it move through there by itself.
8,
Notice we had to make sure that this 2x4 doesn't run into the weight,
No.
so we've got it rotated upwards.
10, 11,
If the phone rings right now, don't answer it. This is a two-man job, we
12.
can't stop. If, however, you do hang up on a
13.
nail or run into a major problem, you can go up and away from the template
14.
and still save the job.
15, 16, 17, 18, 19,
A nice, smooth, even flow. If you're a little bit
20.
behind, don't stop with the wire. Just slow it up until you catch up.
21,
If you stop, it'll burn into the foam block.
22, 23, 24, 25 and going up, 26, 27,
Now,
round the
it's
corner,
important
half
to keep
inch,
it on the nail until we're on the
resting
template
on the
until we're out.
template, and we're out.
Good.
Cut.
Okay, we turn off the hot wire saw and the top cut is done. Okay, now we're cutting the
2 inches.
bottom in exactly the same way
1
that we
inch.
cut the top. Coming up under to the
Half an
nail.
inch, resting on the nail.
I'm resting there, ready to go.
Okay, going in, 1/4 inch, 1/8 on the template, going down. Half A, half B, half 1, half 2,
Now we're finishing up the cut. We're
23,
finishing up the cut on the bottom. The difference on the bottom is we're going to
24.
pause at number 27, which is a half an inch from the end.
25, slowing down, 26, slow down, 27.
We're pausing
Pause.
there.
1,
Okay, now
2,
moving out.
Now going up.
Staying on the template. The pause gives us a nice sharp corner for this flat edge, which will eventually be our skinned top and bottom skin overlap. Okay, now for the unveiling. What have we here? We get the weights off. Open it up. And presto, a full core airfoil section. We notice right here the wire was lifted off of the template for a while, and we've got a ridge, which you can see there. And it's best to take a hard block and remove that ridge, sanding. Get it down nice and smooth before we pull the templates off. Then we get a knife and pull off the leading edge flash. Get the flash off with the leading edge. You have to be very careful on the leading edge to not change the airfoil shape when we round it down. Let's remove the templates first. We very carefully use the sanding block to remove the flash on the leading edge. And don't take off too much. Make sure to keep exactly the right airfoil around the leading edge. And our part is ready to go on to the jigging it for the layup now. Mike has mixed up some 5-minute epoxy, which will cure in 5 to 7 minutes, and he's putting dabs on the table. And we're going to use it to hold down a jig to hold our part securely in place for epoxying, or for applying the fiberglass skins. He's putting some very small dabs on the jig to hold the part securely down. It's important that a part not move around while you're working on it. These little dabs will cause a small bit of damage to the part for the other skin, but it's much better to have the part securely down. We'll line it up like this and bring along some lead shop bags and lay it down. Check to make sure that it's correctly set. This part is correctly jigged now, very flat, and a few minutes later it'll be ready for us to apply the fiberglass skins, and it'll be held securely in place for the glassing. The area of the shop, or outside the shop, that you use to cut fiberglass cloth needs to be very clean, free of any grit or dust or dirt or contaminants. This is unidirectional fiberglass cloth that we use to skin the winglet that we cut out. It's laid out on the table and marked. You take a pair of good sharp scissors. Right now we're setting the fiber orientation, which runs this way relative to the selvage, and the selvage is the edges, manufactured edges of the cloth. We've measured those, and we're cutting the fiberglass cloth that will be used for the skins. Now, to keep the cloth from being distorted when you pick it up, because it can be skewed, it's generally best while it's still on the table to roll it carefully. Lift it up carefully in the rolled position and set it aside, and when the layup is required, your cloth will be not distorted. It'll be ready to lay and roll out onto the part to use. This is a square of bidirectional cloth whose fibers are running at 45 degrees, half of them this way and half of them this way, diagonally. The cloth can be distorted quite readily into a trapezoid in this direction, or into a trapezoid in this direction. And this weave of cloth is very flexible in that way. It's not flexible along the fibers. Fiberglass cloth is extremely stiff. However, the other flexibility requires it, allows it to be compound curve shaped. Notice how it'll make a compound curve there without any wrinkles. Now, when you cut the cloth, this shapeability, which allows nice compound curves, can give you problems. For example, I'm going to cut at 45 degrees. Again, this is a selvage. This is a 45-degree line. The bidirectional cloth is almost always cut at a 45-degree line. I'm going to cut what we call a bidirectional tape. We'll show you later how these are used. But this is a 2-inch wide, or about a 2.5-inch wide tape. It is important to roll it up and lift it up in a roll and take it to the part without distorting it. However, if you pick it up like this, particularly a long piece, notice I've pulled it until it's just barely over 1 inch wide. And I've distorted it. I've made it longer than it should be and too narrow. Now the cloth can be stretched back out to its original width, back out to the 2.5-inch width, and rolled up and taken care of, but you've got to use care on the bidirectional cloth to not pick it up and stretch it and distort it. That cloth now, rolled up, is ready to take to the part of the airplane at which the 2.5-inch width is called out.
Okay, preparation for the layup. Before you contemplate doing a layup, you clean your area. You make sure that there's no foam dust or sand or anything on your table. You want it to be as clean as you can. You need to have all of the tools that you're going to need. Scissors, knives, tape measures, and very important, paper towels. Squeegee. Squeegee is the main tool. Paper towels are very important. You keep your hands clean, you keep the table clean whenever you spill some epoxy, and you can wipe off your scissors or wipe off the knife with a tape measure. One of the things that you need to pay attention to with epoxy, because any epoxy has some toxicity to it, is to protect your skin. You don't want epoxy ever to touch your skin. Ply9 gel is a skin protective material. It just puts like an invisible glove on your hand. Rub a little into your hand, thoroughly cover all of your hand with it. The other method, this works well for some people don't like it. The other method is gloves. And a cheap disposable glove is a really handy thing to use. You don't get any epoxy on your hand with the gloves. And then when you're done with the layup, you just pull the glove off and your hand's as clean as it was before you started. So that's a good method. Okay, one of the most important things about building a composite aircraft is having the temperature in your work area in the shop where you're working has to be between 75 and 85 degrees. It doesn't, no matter what it takes, you do have to bring the temperature up to that. You can't accept less than that. Optimum is 77 degrees. This is the epoxy that is used, the resin and the hardener, and the ratio pump, which this is an example of, will dispense it out in the correct ratio, hardener to the resin ratio. Now, to keep this stuff at the temperature you need, it's better to have a light bulb like we have here underneath it. Brings the temperature up 10 or 15 degrees above the room temperature, makes it easier to dispense the stuff, and it mixes more readily and more accurately. And I'm going to show you here how we mix, how we use this stuff. In the plans, it also calls out that you can do this operation with a balance. And that is something that's covered very thoroughly in the plans, and we don't plan on covering here. Take the pump, ratio out a little hardener and resin. You can see that it's thoroughly warm, so it comes out very rapidly. We stir it up. And what we have here is what we call pure epoxy. Epoxy is not epoxy until the resin and the hardener have been joined together. And you are now causing a reaction here, joining the resin and the hardener, making it into epoxy.
Now that we've mixed the resin and the hardener together and have epoxy, which Mike has here, notice epoxy is a relatively thin, runny mixture of resin and hardener, and that's called epoxy. We call it pure epoxy. We can mix with it an equal quantity by volume of microballoons and obtain what we call micro slurry, which is almost as runny, but it is only about half the density because it has these microspheres. With the safety epoxy material, you must use the glass type microballoons because the quartz microballoons and the phenolic microballoons will absorb the hardener and retard the cure. This slurry will be used later to prepare the foam for fiberglass skinning. Another thing that's used is what we call wet micro. And all it is the same thing we just looked at with more microballoons put in. 3 or 4 times the volume of the epoxy of microballoons is dumped in there and mixed until it obtains a consistency about like heavy molasses. Notice it has a shiny surface still, and notice that it will run and eventually flow down into a smooth surface like very cold molasses. If you continue to mix in more and more microballoons into the epoxy, you'll obtain a mixture that we call dry micro. The reason it's called dry micro is it has a dry looking surface and it stands up like cake frosting or peanut butter. It does not flow and run like molasses. You shouldn't put any more in than just required to give it the dry appearance and to stand up. This is used in filling areas that need to be bonded together like foam blocks where there's a relatively large gap and the wet micro would otherwise run out of it. It's also used extensively on contouring rough places and filling during the finishing process of the airplane. The microballoon mixture, the wet micro and dry micro, is not very strong structurally. It is plenty strong in joining foam blocks because it's considerably stronger than the foam core material itself. But there are some areas where we need a filler that makes the epoxy mixture much stronger. And that is obtained by taking the pure epoxy, again thoroughly mixed first, and adding cotton flocks, which is flocked cotton material. And that material is mixed in with the epoxy and it becomes a material with considerably different consistency than micro, and it's called flocks once it's mixed in, and it is used in structural places as called out in the airplanes. This would be called wet flocks pretty much because it is runnable. If we mix in just a little bit more of the flocked material, it'll stand up, and just like frosting, very much like the dry micro did, and it's called dry flocks or just flocks. Due to the limitations of the size of the styrofoam blocks, very often you have to join 2 blocks together. There's one very excellent way of doing this, and we'll show you all the steps involved in it now. It involves spreading a very thin coat of micro slurry, which I've already done on this side, and Mike is using a squeegee and spreading the thin coat of micro slurry on the other side. Just a very thin coat. Then you take wet micro and make a bead right down the middle of one of the blocks. It's important that the bead be in the middle because when we squeeze these blocks together, the epoxy then will work itself outboard, driving out the air as it goes. We position the blocks over each other, we hold them securely, and then we wiggle them back and forth like this. Now the epoxy is slowly moving out to the edges and driving out the air with it so there will be no voids. When they're in position, they can be nailed together, generally put into a jig depending on what is being built. And it's important to go along and wipe off the excess epoxy that may make it to the surface, because if any contouring has to be made later, that will disrupt our means of contouring that. You'll notice the epoxy has driven out towards the surface. If there's a small void there where it's not completely filled, that's not of concern. It can be left open, and it can be filled immediately before the fiberglass skin is laid over it, which is a much preferable way of doing it.
Okay, what I'm going to show you here is a basic fiberglass layup on some PVC foam. The piece of foam has already been positioned. We've glued it down with 5-minute little spots of 5-minute epoxy, and we have all the fiberglass cut out, and we're ready to go on the layup. First thing you do, pour on slurry. Don't fool around putting it on with a paintbrush or something, you're just wasting your time. Pour it on, move it around rapidly using a squeegee. Cover all of the surface that you're going to be using for the part. If this was a front seat bulkhead or something, cover the whole thing as rapidly as you can with the slurry. Don't be afraid that you've got too much on there, because you can take it off again. Get it thoroughly covered. The slurry, of course, is going into all of the imperfections in the surface, the broken cells that are on the surface of this piece of foam, and filling those voids with a lighter material than pure epoxy would be. So you take off any excess slurry, and you should have a uniform surface ready to put the fiberglass on. Get your fiberglass, be careful not to disrupt the fibers. Put them in the correct orientation. Fiber orientation should be correct, and that is clearly stated anywhere in the plans on the part that you're making. In this case, I have the fibers running diagonally across this square block. Spread it out with your hands. Make sure that you get the fibers as straight as you possibly can. You do not want to have the fibers oriented, twisted like that, or curvy, because they don't develop any strength until they're straight. So put it on and take time to be sure that you do have the fibers running straight in both directions. This is bidirectional. Excuse me. Pure epoxy with no micro balloons in it. Again, pour it on. This is where the paper towel comes in handy. Clean up your squeegee. Move the pure epoxy around. The whole purpose of this is to get the glass thoroughly wetted out with the epoxy. So you move it around. It takes a minute or two for the epoxy to wet the glass. It'll take all of the shiny silveriness, the silvery look of the glass will be gone when it's thoroughly wet. Move it around. If you get too much on there, way more than you need, then you can easily take it off. We just have about the right amount on there this time. I'm going to be putting a second ply on this, so I won't take the time to prepare that as if it was a finished one. I'll put this second ply halfway across so that I can demonstrate the peel ply transition between this ply and that ply. Again, all the fibers want to be straight in the direction they're running. Pure. Work rapidly, but don't kill yourself. When you're doing a basic layup like this, it should take you no more than 2 minutes per ply per square foot. This is about a square foot, so we should take about 3 minutes to do this layup. And you can see this side here is now thoroughly wetted out. There are no silvery strands in that at all, whereas there are on this side. We just add a little bit more in that area. I found it easier if you just add more epoxy than you think you need, move it around and let it sit for a minute or so. And it will soak into the fibers and wet it out, and you can easily remove excess epoxy with your squeegee. Just a little more silvery fibers right here. There we go, it's wetting out nicely. It's looking good. Now, remove some of the excess epoxy that we have in here. To test whether you have excess epoxy in the layup, take your squeegee, draw it across the layup, and stop. At that point you can see that we have some a mound or a little ridge of excess epoxy there. That's not acceptable. If you leave that on your airplane, it could be 20, 30 pounds heavier by the time you get done. So take your squeegee, take it right off the edge. Better to be on the floor or on the table than on the airplane. Now you can easily overdo this. You can end up getting the part too dry. So lots of light, not too firm, strokes with the squeegee will get it off. Okay. Look at it in the light. Make sure that there are no silvery strands of dry fibers in there and no pools of epoxy where it would be too wet. That's a good looking layup there. Now I'm going to show you the application of peel ply. Peel ply is a Dacron surface tape that will not stick permanently to the layup. Where we have this transition between this ply and that ply, we have some sharp little edges of fiberglass that when they cure will become literally like needles, and you'd run your hand into them and they'd stab you. To get away from that problem, take some surface tape, Dacron surface tape, lay it down so that it covers the area, and add some epoxy to it. You don't want to try to wet the surface tape out by drawing epoxy out of your layup. We assume you have a perfect layup here. The ratio of the resin to glass is perfect. Now if you add this surface tape to that and try to draw it out, you're ruining the layup underneath. So add some epoxy to the surface tape. Weight-wise, this is not a big problem because you will be pulling the tape off after it's cured. Now what we have here is a nice smooth transition between this ply and that ply, and when that cures and we peel this peel ply off, we'll have a very smooth transition and no sharp edges that would stab you in the fingers. Okay, now before you go away from any layup, really carefully examine it. It's a good idea to have a trouble light or something and look at it in all kinds of light and make sure that you don't have any very wet areas or any very dry areas. When you get the glass, the basic layup over the piece of foam that you're doing, you cannot leave it this long where it's sticking over the foam. You need to scissor trim it to 1/4 of an inch. Each ply needs to be scissor trimmed to within 1/4 of an inch of the edge of the foam. This will stop the weight of the foam that's hanging off the edge from pulling the layup, lifting the layup and forming a little bubble along the edge. If you've got a lot of excess weight here, it hangs down and it raises the foam just inside the edge. If you scissor trim it like that, you won't have that problem, but you do disrupt the fibers when you do that. So you need to come back with your brush and stipple them back down, get all the fibers back in the right place when you get done with the scissor trim. At the same time, you check to see that you have wetted the glass layup up beyond the edge of the foam. You can see the edge of the foam. You wet it up thoroughly beyond the edge of the foam. The reason for that is that you're going to be coming in here later on with a sharp knife and trimming right to the edge of the foam. If you don't let the epoxy go into the glass, it'll be very difficult for you to knife trim it, and it will also possibly leave you with some dry fibers right in close to the edge.
Okay, now this has been in cure for 4 or 5 hours. It's still tacky. If you push down on the sides, it feels about as stiff as a stick of chewing gum. If it's much flexible or more flexible or not cured any more than that, it'll be difficult to knife trim without disrupting the fibers. If it's fully cured, it'll be difficult to get the knife through the epoxy, and you have to face with having to saw it and then sand the edge. However, since we've caught this at the right time, it's a very good time for knife trim. Trimming that to the edge means that all you've got to do is stick the knife blade in, carefully go across it, and remove the excess, and you have a smooth joint. You want to be careful not to slip during knife trim and go in. You can ruin the part and require a structural repair. But that's all there is required. There will be no sanding in general required on that. In the next sequence, we're going to show you how we're going to glass or skin with fiberglass this core that we cut out, which will be the lower winglet of the Long Easy. We have it mounted firmly here, and we rounded the edges so that it'll have a nice round shape. This is the upper portion. This is a trailing edge. You might be wondering why this has this notch at the back and why it has this big piece of excess foam left along here. Here's the template for that. This notch in this area that you see here, in this area, is parallel to this skin, not this skin. And this transition line would run parallel to it. This excess foam is left on here so that the foam core will be rigid during the glassing instead of wavy because it's very thin back there. Let's go over to the drawing board and show what's happening here. This is the top skin, and it has this long excess foam left on it. Notice that this transitions to this area, which will later on be a skin overlap. The first skin that we put on will be this skin, and it will be stippled down into here and knife trimmed at this point. This is a trailing edge of the wing. It's important. Right here is the trailing edge reference. After this skin is cured, we will be turning the wing upside down, and we'll be cutting off this portion right along this line. Then we will skin the other skin, and it will give us an overlap in this last 6/10 of an inch. Later on, we'll come along with some dry microfill, which is a lightweight filler, and fill this area. This gives us a very preferable structural overlap at the trailing edge. To facilitate this, and to make it easy to remove this foam before putting on the second skin, before skinning the first skin, we're going to put peel ply right along this face, and we'll show you how nicely that allows you to put on the second skin without damaging the first skin with sanding. Okay, now we're getting ready to skin the first skin on the lower winglet. First of all, we'll make sure that it's perfectly smooth, there's no ridges or bumps, and that it's perfectly clean. We've blown this off or vacuumed it off with a vacuum cleaner. And we're going to take the hard block and make sure that this edge is nice and smooth. We've got to be careful not to undercut it, but then again, we don't want a large radius or a rise in this trailing edge overlap. This back face is our reference trailing edge. We've got to make sure that it's kept intact and is good and straight. Mike is going to spread slurry on this just as much as he did the PVC layup. And I'm going to put the peel ply down along this trailing edge area. Now the peel ply will disappear and move out of there and fall off the table while we're skinning it if we don't hold it with something. So I'm putting these very small little brads down into the foam in 2 or 3 places. That'll keep the peel ply in place. Notice we don't want to get slurry down in this area because we should never put microballoons between fiberglass structural layups. They go only between the foam and the fiberglass itself. So we won't put slurry down in this peel plied area. Now that we've put the slurry on here and we've put some duct tape around the edge to keep epoxy from running down and onto the bare foam surface on the other side to protect it, we're ready to put the glass on. We'll lay the glass down, roll it out onto the surface, and then start pulling it tight. It's very important that the orientation of the fibers be correct. Our fibers now are 30 degrees this way. The next ply will go 30 degrees the other way. Now we start from the middle and pull outward, pulling the fibers tight. Let me describe how to take a wrinkle out if you get it, by making a wrinkle. Notice there's a wrinkle here. You go way out to the edges and pull on the fibers until you finally find them. Notice how it'll disappear. Way out at the outsides, if you pull and stretch the fibers, the wrinkle disappears. That's the best way to take care of it. Start in the middle, work your hands outboard, pulling the fibers tight. Think of them as little rubber bands that you want to leave all nice stretched tightly and not crooked. We bring the whole part down as flat as we can, and then we bring in the excess epoxy later.
Okay, now that we've got the fibers straight, the orientation correct, we pour on the epoxy. Just pour it on like we did on the other piece. Move it around with your squeegee. Do not try to put it on a little bit at a time with a paintbrush. This is some of the builders have been trying to do that, and it's a very silly way to do it. It takes forever, and you don't get as good a job.
I'm going along and scissor trimming the ply back a 1/4 inch away from the edge. There's another ply that will go on this, so it's okay to leave it excessively wet until we get the second one on. In fact, it's better to have it wet and to have the epoxy soak up through the second ply rather than to have it dry and try to get epoxy down through the second ply as the air is coming back up.
Okay, in an area like this where you have a little joggle or a curved area like this, it's fine to have a little excess epoxy. In fact, you're better to be a little excessively wet in an area like the trailing edge.
Now it's okay to leave extra cloth on these areas where they come straight down and hang straight down. In fact, it helps the glass stay down against the surface by the weight of it. Whereas over here where it comes straight off, it's best to scissor trim it within a 1/4 inch. So leaving excess on here and a 1/4 inch excess over here is the preferred method of trimming. Okay, now we've got plenty of excess epoxy on here. The fibers are still straight, and we're ready to go to putting on the second ply. Being careful, again, about ply orientation, we lay down and roll out the second skin. The first skin went at 30 degrees this way. The second skin's going 30 degrees crossing. So the relative angle is 60 degrees to each other. Fiber orientation is very important. Like the second ply, like the first ply, the second one is being made very straight. The second ply is always much easier than the first ply. It's easier to go over a piece of fiberglass than it is to go over foam. So this will wet out quicker, straighten up in less working time. And we may have enough epoxy on here right now to wet this out. Mike will determine that with a squeegee. Although it's not a bad idea to add some excess and then take the excess off. It generally works much faster. Again, inspecting for straight fibers. Notice that we've got the entire piece relatively wet out, and then we'll go and work in one area. And while we're working towards the other areas, they can soak up the resin and soak up the epoxy and get further into their cure. Right now we are striving to get the dryness out. We're looking where there's areas that are white. We're looking in areas where the epoxy has not yet fully whitened, wetted out the cloth. We're not really worried about the excess epoxy in it now. Right now we're concentrating on getting the adequate wetness, and then later we'll concentrating on removing excess resin, and that's the correct order to do these things.
On the curved parts, the edges of the part, again, it's a good idea to have a little excess wetness.
The best technique out on big surfaces, again this is a relatively small part, but on big wings and so on, is many light passes with a squeegee. Don't pull real hard. You can pull the fibers and disrupt them. You can even stretch them enough to draw in extra air. Now we've got excess epoxy in here. Let's do a too wet test by bringing the squeegee. You should do this on every layup. Pull it 6 inches or so and stopping. And right in here I can feel a ridge of epoxy down between the plies. We'll always pull a little off the top. Get rid of that lightly with your finger. And I can feel a little ridge which shows us that there is excess epoxy between the plies. That must be removed. So I'm going to spend some time doing like this. Notice I'm working with my other hand to keep from moving the glass excessively around. And I need to have the cup to get that excess off onto the cup so I don't keep bringing it back into the part. Right now is where you're doing the quality on the layup. Right now is where you're determining the correct resin ratio, the correct ratio of epoxy to fiberglass. And this fiberglass weave allows you to do that very accurately by just making smooth passes with a squeegee like this. And it will assure you that all the excess epoxy is off, and it'll give you a ratio which is results in the weight of the finished product being just slightly, mostly fiberglass, and maybe about 40% of epoxy by weight. This is where the quality is done. This is where the resin ratio is determined. Not with a brush, not with any other means, but the squeegee and smooth, light passes like this. When it looks perfectly uniform, perfectly good, no dryness, and it passes the test, there's no ridge there, then you have the layup correct.
We're going to apply peel ply to this part that we finished now. The reason, again, for putting peel ply on is whenever you put a part later on, after this is cured, it will be attached to another part of the airplane that is already cured. And in order to do a structural layup between the two, it's a good idea and saves you a lot of sanding to put peel ply on it. And this is Dacron surface tape we call peel ply. Just reel it out. Cut it off. Now while we're putting it along this edge, this is the root of a lower winglet, and this will be joined to the upper winglet. And when we do a structural layup across here, we put this peel ply on, and it prepares the surface of the epoxy for us to be able to do a good structural layup over the top of it without having to sand. Sanding on cured fiberglass is really an itchy business. Get a lot of dust in the pores of your skin, and there'll be plenty of places where you have to do that. But when you do wear a dust mask. But you can save yourself a lot of trouble by doing this wherever you even think there's going to be additional layups done, like Burt's doing there, where the skin on the bottom of this wing comes around and laps onto this. You can save yourself sanding in that area. Now when you're putting peel ply on, do not try to wet the peel ply by sucking epoxy out of an already perfect layup. If you try to sit here and stipple epoxy out of the layup, you're robbing a perfect layup of epoxy. And so you're getting a starved layup. Here we add a little epoxy. This excess weight of epoxy will be peeled off when we pull off the peel ply.
The peel ply does not go around compound curves very well, and if trying to get it around here may raise the fiberglass layup, which is otherwise perfect. So it's best just to omit it from there and have to sand that area during the next skin layup. After putting it on, double check that again we have excess wetting beyond the surface to allow a knife trim, and also to make sure that we don't have dry fibers right at the surface, which is a common error. Make sure that it's wet beyond. Make sure again that our layup is perfect, that we don't have fiber disruption, that we don't have excess epoxy, that all the peel ply is wet out properly, that all the excess epoxy is pulled off of the part. Make a good look at it. This is the important inspection time, because once it cures, then you have a structural repair that generally adds weight and is a difficult thing to have to do. But if the layup is left well inspected now, and it's generally good to bring another set of eyes in, get someone else to come in and look at this, not just the person that built it. Get someone else to take a look at it, because he can generally see things that your eyes will overlook a dozen times. If there's a bubble or something, he may see it and you won't. If there's excess epoxy on there, he may point it out and you won't. So get someone else to look at any critical aircraft part while it's still wet and can be fixed easily.
And do use a bright light. A trouble light held at an angle when you're examining a layup for a final inspection before walking away from it is an excellent idea. It'll really highlight the dry spots or even wet spots.
The most important time is right now, because once we walk away from it, we're stuck with what we've got. Well, now it's a couple hours later, and this layup has been allowed to cure to where the fibers are relatively stiff, and yet it's still tacky. This is the perfect time at which to apply the dry microfill in the trailing edge. This will mean, if we do it now while it's still tacky, that we don't have to put it on later on, and we don't have to ever sand it. The best way to do this is just to lump it on roughly like this, and to lay a piece of peel ply over it like this, and then take the squeegee and move it with a few light strokes along like this to level it completely out. Don't push it down below level, or you have to add some more later. If you don't put the peel ply over it, the dry micro tends to roll up and cause voids as you're trying to level it. So with just some nice passes like this, it levels out the dry microfill perfectly, squeezes the excess out the ends where it belongs, and make sure that the trailing edge is not bumpy because of your dry microfill. Right along the trailing edge, it's squeezed down to nothing. I can see the foam. I can check to make sure that it's perfectly straight, because that's our reference trailing edge. If we take a good straight edge, if this were a long wing, take a real long straight edge and put on there and make sure that it's perfect. After cure, we can grab a hold of this and just peel it right off, and we'll have a perfect microfill of the trailing edge. Well, it's at least a day later, and we have a full cure on the surface and on the skin. We can take the peel ply and get under the edge and remove it, reveal that we have the nice microfill. And I'm going to remove the peel ply around these edges also, because the next job is to glass the other side, and we'll need to lap onto these. I'm not going to remove this peel ply now, because this is removed only just before the entire winglet is mounted on the airplane, and we need to lap up onto that. Next step is to break loose the winglet from its jig. We're breaking it loose from the table, and if we can get it off of here. We'll have some minor foam damage where it was glued to the jig, and it's easily repaired. Now we're going to find the piece of foam. Oh, here it is, right here. This is the piece of foam that it was cut out of on this side. We'll lay it over here and determine what size it is, marking around it. And then we'll go in and we're going to cut this piece of foam at least 2 inches smaller inside here, and use that as a jig to hold this. That allows the new skin to lap around here without interference from the jig. We now have our winglet upside down, jigged in place. Not quite ready to be glassed yet. We've got to remove this trailing edge hump. We've got to remove the peel ply that's in here so that our glass skin can be laid down perfectly. The best way to do that's in 2 steps. First of all, we take this hacksaw blade and we saw it off. leaving 1/8 of an inch of foam or so on it. Little things I ran into there were the nails that were holding the peel ply down. Now I'll grab a hold of the edge of this peel ply. Now we have a perfect surface. I won't touch it now because it's ready to be laid up over. It does have an edge, a lip on it here, which will need to be sanded down. And of course we've got to transition this in. A hard block is the best thing for transitioning that. Be careful here not to cut down into the skin because you'll damage the strength of the skin that carries onto the bottom side. We now have foam that's transitioning right off smoothly off of the foam core and onto the skin overlap area. Our next job is to carve this rounded edge here, and then we'll be able to glass. So we'll get started with that with a butcher knife. Give me a hand here this knife. Generally I'll get a diagonal cut off with a butcher knife and then finish up with sandpaper. From this area forward, the glass skin will be able to go around the skin and on, lapping onto the other side. Back here, though, it's too sharp for it to go around. So we're going to remove some foam locally. Get that out of there. And before skinning, we will trowel some flocks in here so that when the skin comes over, it'll just butt to the edge, but it'll have flocks in between and it'll provide a strong joint even though the fibers do not run all the way around. It's important to inspect for areas, particularly down here where the glass will have to make a sharp turn. Glass will not make a sharp turn around a sharp corner, and if you have anything that's an edge that needs to be radiused, you must do it before you start glassing. So we'll take these areas and round and transfer any of these areas that need to be rounded nicely. We'll clean up, make sure that we have all the dust. Make sure we have all the dust off the surface. And now we're going to go and make some little repairs. Remember the little dings that we had because of the foam being joined? Mike is going to paint a little bit of pure epoxy down in there, not very much, but just a faint little bit to wet the surface and to make sure we have good adhesion, and then we'll fill them with dry micro. In fact, it's good just to wipe it in with your finger just to get a little bit of a little bit. If we put a lot in there and then put dry micro in it, it'll mix with the micro, make the dry micro into wet micro, and it'll run out. So it's important that we wipe off all the excess, but just a little bit. Also, there's some areas where we've got some dings and some low places in here, and we'll also put a little bit of pure in there and come along and get the dry micro fixed on it. Here again, the dry micro will just make a nice fill of these low places. Doesn't require a lot of work to put it on. We'll come along. I'm being careful not to get micro down onto the other glass surface because we don't want the micro between the two structural areas of glass.
And in this area where we have a glass-to-glass layup, where the second skin laps right directly onto the first skin, you don't want any micro balloons in there at all, just pure epoxy.
Mike's putting pure epoxy on that. Remember, the rest of this whole surface will be slurried, just like the front surface was, or painted with micro slurry. But we don't want to get slurry down onto the other areas. go around even little nail hole dings, it's a good idea to fill them now. Do not do this the day before the layup, because if these are cured, you'll have a mess trying to glass over it smoothly. This is only done just before the layup.
Now this void that Burt was talking about before, we've painted some Pure in there, and now we're going to trowel in a little flux, little wet flux, which is a structural material, very, very hard material. This trailing edge here is the tip of the vertical when the airplane's standing up on its three wheels, and it's subject to getting banged into when you're moving it in and out of hangars, and it's a good thing to have it nice and strong here, so we put flux in.
I'm also going to paint the Pure epoxy down on the first skin underneath. I'll do this initially so it'll have time to tack just a little bit, and it'll help retain the glass when the glass is being rolled onto it for the overlap joint that's required underneath. It's important that that be a good structural overlap, particularly at the leading edge along a wing. And we'll show you how to do that in a minute here. Mike's putting on the slurry now.
Be careful not to get any of the micro balloons in this area where you have glass to glass. You do not want micro balloons in.
Otherwise, the slurrying of this surface is identical to what you saw on the other side. Now we've laid on the first skin on the second side. I'm trimming it closely for scissor trim at the trailing edge and also along the side here. But down on the bottom side here and on the leading edge where we'll have an overlap, I'm leaving on the amount of cloth that's called out for on the overlap. In this case, just 1 inch. 1 inch beyond where it picks up and starts lapping onto the first skin. And remember, when we get to this point here, we're unable to overlap, so we'll scissor trim back around. Now we'll try to work this cloth underneath, and it'll stick very nicely to the first skin that was on the other side. As the first skin, we'll look carefully for smooth fibers, pull out any problems, pull it underneath, stipple it up, and we'll bring in some more epoxy, which will help us make things stick underneath here.
Where the glass laps up underneath onto the first side, you want to add a little epoxy there to make sure that it's thoroughly wet. You cannot afford to have it dry there, because that is a structural closeout of this particular part.
Once it's thoroughly wet, we can come by with a squeegee and very easily remove excess, but we want to make sure that it has plenty to start off with.
This is called stippling. Take your paintbrush, pure epoxy, and stipple it into the cloth.
Once it's wet out and down good, we'll be ready to put on the second ply of fiberglass on this second skin. Our fiber orientation is this direction. Now we'll need to go this direction. Okay, double checking the orientation. That's good. Laying the cloth down and proceeding very similar to the first side, except for our now problem with scissor trimming to the right dimension and lapping it up underneath. Otherwise, we're very similar to what you've already seen. It's important to have a good look underneath the leading edge. Make sure that your overlap stays down and is good. You can take the squeegee also. It's a little difficult to reach on this part. You can take a squeegee generally on a wing, or even a roller, like a paint roller, disposable. You throw it away after you're done, and it's very handy in assuring that the leading edge overlap is beautiful before you leave. And down without any bubbles here. You've got to get underneath there and look at it closely, because it's easy for a bubble to be there if you can't see well. So you've got to get down and take a good look and make sure that it's fine. Mike's putting on the peel ply for the layup afterwards. And while he's doing that, I'd like to explain what you have to do if you don't do peel ply. In other words, I'm going to take a little area of fiberglass here and assume that later on we're going to have to make a structural fiberglass layup over it. And we did not peel ply it. First of all, let's see how easy it is to prepare the surface if we had peeled plied it. That's all you have to do. That is now ready for a structural layup. Now I'm going to show you what you have to do if you did not peel ply. You have to take 36 grit sandpaper. It's generally best to fold it twice, then it doesn't move around. Fold it once at 1/3 and once at 2/3, and it doesn't move around in your hand while you sand. And start to work here. This little area that I've been working on here is about this big. And if you look closely at it, only about 2/3 of it is sanded dull. The rest of it is shiny down inside the weave. This is not yet ready for structural layups. Let me try it some more. Now, only the area that I'm going to circle is adequately sanded for a structural layup. Actually, just right there. I did quite a bit of work, and I generated a lot of sanding dust from fiberglass that is itchy, just to do about 3 square inches of sanding. Notice how much faster the peel ply was. If you forgot to put the peel ply on an entire leading edge of a wing, for example, you would have to spend that much time on each square inch to get it correct. Also, you have damaged the strength of the top ply of fiberglass, and your structure is not as strong. So it's imperative to use the peel ply everywhere that it's applicable. In this section, we are going to be covering several different special layups. The first one will be a shear web. Mike will explain to you how we do the shear web, which might be inside of a flying surface such as a wing.
Okay, what we have here is a simulated section of a main wing on a long easy, or even the canard on a long easy is done the same way. This is depicting a C-spar, and we have this is the body of the wing. The cutout for the spar caps will later on run in these troughs on either side of this here. Coming across the top of this in the shape of a U or a C will be the shear web, which is generally 2 to 4 to 6 plies of unidirectional glass that cross each other to tie the two spar caps together in shear. We've prepared this piece of foam by slurring it in the area that we're going to do the shear web layup, and we've also protected the rest of the wing with gray tape or duct tape, so that when we're doing this layup here, we don't spill epoxy onto the foam below, or which will be the top and bottom surface of the wing.
Just for demonstration purposes, so that you'll be able to see it, we've shown the fiber orientation of the cloth on the with ink marks. It's not a good idea to do that because the ink disrupts the performance of the epoxy. But notice it goes 45 degrees. A little bit more there, isn't it? It should go 45 degrees across the shear web face. And also 45 degrees down this face. And as on the other layups, the wrinkles must be pulled out straight.
And the straightness of the fibers are really important in the shear web. You're taking tremendous loads in a shear web. The glass cannot take the load unless it's straight.
Notice we made the glass quite a bit too long, and now we'll just scissor trim it. It's okay for it to be a little bit short. If it's too long there, it will build up into the corner and cause a disruption that'll be hard to, it'll get in the way of the spar cap. Get some epoxy on this.
If you just take your finger and run it into the corner, it'll crease the glass, then you can pull it away and cut just short of the crease. It's better to be a little short than to fill this. You do not want the glass to run up into that little corner. You can be as much as a ½ inch short without any problem at all.
On a shear web that's made from unidirectional cloth, each alternative layer is crossed at 45 degrees to the last one. Notice now this ply will be exactly 45 degrees, roughly 45 degrees orientation relative to the first ply. And it'll be applied and scissor trimmed just like the first one was. I may have said 45 degrees to each other. I meant 45 degrees to the axis of the shear web or the axis of the spar cap. Actually, they're closer to 90 degrees to each other. The importance is that each alternate layer crossed. Now, of course, being a shear web, it'll eventually get glued to something else here, and eventually the spar cap will be glued to it here. So after the layup is perfect, you're going to want to go along and peel ply the entire piece. And that's all there is to a shear web. The next specialized layup we want to show you is the spar caps. Spar caps in these airplanes are generally made from unidirectional E-glass, and it comes on long rolls. In this case, it's about a 25 thousandths thick, 3-inch wide unidirectional tape. It's relatively heavy compared to the cloths that we use and requires more patience in wetting it out. And we'll show you a special technique that we use in doing that. And we built a simulated shear web here, and we're going to be laying several plies of the spar cap. Of course, the orientation of the fibers is this way, and they're tied together by some very small fibers in the lateral direction. So we generally paint a liberal coat of epoxy down onto the shear web, just a good, real thick coat, and we'll lay the spar cap down. Now this generally goes the whole length of the wing and then tapers off to shorter pieces as the spar cap gets built up. But for our sample here, we'll show it just in a smaller piece. And again, we work from the middle out and pulling the fibers very straight. It's very important that the fibers get pulled out straight. And we use a shortened version of a squeegee that will fit down into the trough to pull the fibers straight. Notice just a few passes of that squeegee. That's all there is to it. The fibers lay down very nice and straight. Paint on a little bit more epoxy on top of that. We'll get the next ply down. It's important to squeegee about every 2 thicknesses of this to get out the excess epoxy. Don't put all of it in and then expect to get out all the excess because it may be impossible to do so. Now, because the fibers, the bundles are in bigger groups, they'll take longer to wet out. And to assist in wetting out, you can use a small hair dryer if you use caution not to get too much heat on the adjacent foam surfaces. So Mike will turn on a little bit of heat there.
Just warming it up will cause the epoxy to become more liquid, and it will wick into the bundles of unidirectional fiberglass. You can just see it getting wetter.
You should work on the spar cap about 2 plies at a time. Get 2 plies down, get them wet out perfectly, getting them looking just right with the right resin ratio, right epoxy to resin ratio. And when it looks perfect, then you put on the next 2. And sometimes there's buildups as much as 15 or 20 plies, depending on how big the airplane is and how far inboard on the spar cap you are.
That's good.
Still a little dry. A little more heat in there will allow it to soak up the epoxy. We've got a little more required here in the corners. Get a little bit of heat on it. Make sure that it wets out well before you continue with the 3rd and 4th ply.
If it's too hot for you to hold your hand under it, it's too hot to be putting it anywhere near the foam. You should be able to put your fingers under it without burning yourself.
Okay, now that is wet out well under the glass. So again, I'm painting a liberal coat on the last one and putting the next one on. And again, most important motion with this is a drawing with a squeegee from the center outboard to pull it out. If we walked away and left this for about 5 minutes, it would probably wet itself completely out because there is enough epoxy there. So you want to use some patience, use a lot of light strokes with the squeegee, always in keeping in mind that your primary job here is to provide adequate wetting without excess epoxy and keeping the fibers as straight as possible. That's plenty of epoxy. Spend a little bit of time with the squeegee and the hair dryer, wetting it out and removing the excess off the ends. If this is done well, the thickness buildup should be very predictable. It will be very, very close to 25 thousandths of an inch buildup per ply of spar cap. Our next special layup is going to show you the typical corner tape, as it's called, in the corner of a fuselage to bulkhead juncture, or any area where a plane comes together, like a side console and so on. We have already removed the peel ply from this edge. We're going to take it off here. We're going to trowel flocks along here, put it together, nail it together, remove the excess flocks, and immediately put in what we call a corner tape. Mike will put the flocks on, and I'll get this peel ply off of here.
When you put flocks on, put a liberal amount on. You can always wipe it off. Remember, flocks was flocked cotton mixed with pure epoxy to a wettish consistency. Put the two pieces together as if you were putting a bulkhead onto the side of the fuselage. Squeeze them together.
We're going to use nails to temporarily hold them together here. The nails go down through the foam. And we come along here and wipe off the excess flocks. Now, if we were to let this cure at this point in the game, we would have to come down later and sand that edge to be able to put the corner tape in. You want to paint that in there, Mike? The corner tape is a bidirectional fiberglass that has 45-degree orientation. I'll put the orientation on this so that you can see. Half the fibers run this direction, half this direction. Mike has that all wet out. We'll put the corner tape in like this. And there's not too much use for a squeegee in this because it's difficult to get in and squeegee out. And when you squeegee, it tends to pull it away from the corner. So stippling is used almost exclusively here. And we try not to put in too much excess epoxy to start with. And then you will not have the need to use a squeegee to take out the excess.
When you're stippling, you don't bang like that with the paintbrush. You put the paintbrush down and you raise and lower the heel of the brush. This smears the epoxy on and helps drive it down into the fibers to wet it out. You can see that's getting thoroughly wet there. Still dry up here.
Now we have another candidate for peel ply on this corner tape, and that is the transition of this rough edge. If the rough edge is not transitioned with peel ply, it'll be susceptible to a delamination. So we put the peel ply down, use a little bit of extra epoxy. In this case, there's enough extra on there to wet it out. And we go back up to this corner. We need a little more on it, probably. It's dry in the middle there. Bring this up.
Apart from anything else, the peel ply transition inside of your cockpit, where you're going to be looking at it every time you fly the airplane, makes a really neat finish between the corner tape, the structural corner tape, and the surface of the inside of your cockpit. You can really clean it up and make it look neat.
Of course, the peel ply is not left in there. It's removed after the cure. The transition peel ply tapes can be removed immediately after cure.
It looks good. At the end of each layup session or each day's work, whatever you're doing, you end up with cups, several cups, sometimes one or two, sometimes a bunch of them. Like this one where we had dry micro in it. And if you just let that cure the way it is, then you have to throw the thing away. It's useless to you. If with a little extra work, a few minutes taken at the end of each day, you can save a cup like this. Take your popsicle stick, scrape out the excess. And if you have any excess pure epoxy left, like we do here, you can pour it into this cup. You're going to throw it away anyway. Pour it in there. Swirl it around in there and let it set that night to cure. Leave it sitting flat. It will cure with a flat bottom and smooth cup, just like this one will. And then you can reuse these cups after a 24-hour cure. Same way with a flux cup. Take that, throw it away, pour in a little excess pure epoxy and save that cup. You can use these cups over and over again if you do that. You don't have to go through hundreds of them. Now your squeegee is a very important tool, and you should really look after it. If you ever let the epoxy that we have on here cure, you've got a problem. The thing becomes as stiff as a board, and then you can't use it correctly. So after each session, at least, or even during the session, take your paper towel and wipe that thing down thoroughly. At the end of the day, it's not a bad idea to dip the paper towel in a little MEK or something, solvent, and wipe that thing off very thoroughly so that it remains pliable and clean with a smooth edge for doing your squeegee work. The scissors, same way. We have epoxy and micro all over our scissors here, and these are expensive tools. And if you take a little time each day to keep them clean, a little MEK on a paper towel, and they'll last the length of time it takes you to build the airplane. If you allow it to cure on here, the thing will get to the point where you can hardly even use the scissors. Even with the popsicle sticks, if you scrape them off, you can reuse them. There's no need in throwing away all of this stuff. In fact, they work better the second time. They don't absorb anything. Reuse your equipment. As far as your own personal hygiene, now is the time that I just had Plinine on my hands. I never had gloves on. You take them, go inside to the sink and wash your hands thoroughly. Every part of you that's had epoxy on you, you need to wash very, very thoroughly. Burt had gloves on his hands. He was smarter than I, and his hands are not even dirty.
After a while, you'll become disciplined in working with these materials. When you first work with them, you may have epoxy on your hands and you'll scratch your ear like this. After you've done several layups, you'll find it's best to scratch your ear like this and do like this instead of like this. It's also a good time now to clean off your workbench, because now the epoxy is not hardened yet. And if you wait till the next work session to clean off your workbench, you'll be chipping off hardened epoxy instead of just wiping off epoxy that will come up easy now. Sweep the floor, get it ready for the next work session. A clean shot makes a clean, attractive airplane. A dirty shot generally makes a dirty airplane. Finishing the composite home-built airplane is a subject in its entirety that's really beyond the scope of this presentation. Finishing is very important on these airplanes because in the finishing process the final smoothness of the contour is added to the airfoils. The builder must be very careful that he not damage the structure with the sanding block. The structure must also have a ultraviolet barrier applied so that the sun's rays don't deteriorate the epoxies. And they must be painted white so that their structural temperature stays cool enough for the materials used. The details in the finishing are published, and the builder must be careful to follow very closely the finishing requirements. There is a new state-of-the-art, a construction method that is better in many ways. With it, the builder has new dimensions, new capabilities, and his flying takes on new dimensions, and that's what it's all about.
Okay, you can start the camera now, coming through. Okay, we'll be in and break in about 10 seconds. You ready?
Okay, go for it. Okay, camera silence.
Very nice.
Yeah, that looks good.